All right, welcome to the Harmonic Motion Assessment Go-Over video. Hopefully by now you've taken the Harmonic Motion Assessment. If you did not, you can always have the opportunity to reassess, and whatever grade you get will replace your first grade. If you didn't take it and you ended up with a 0, then this will serve as your grade. So let's just jump right into it. Here's the picture. It says the block above is oscillating back and forth between points A and C. So it's sliding out to C and back to A and out to C and then back to A. It says the mass of the block. It says the mass of the block is 0.5 kilograms. And it says that the spring constant here, little k, is equal to 50 newtons per meter. All right, sounds good. So number 1 says, what happens to the speed of the block as it moves from A to C? Well, since the block slides like this, it slides to A and stops, and then speeds up through B, and then slides to C and stops. And so I think the speed going from A to C, I'm going to say it increases to B and then decreases to C. So pretty simple. The speed increases as it goes from A to B and then decreases to 0 as it goes from B to C. All right, let's look at number 2. Number 2 says, what happens to the acceleration of the block? I think to look at the acceleration, I think one of the things that we should do is we should draw a force diagram and look for the unbalanced force. So let's look at A, B, and C. So when it's at A, we know that the Earth is pulling it down. The surface is pushing it up. So this is the force of the table on block. This is the force of the Earth on block. All right, and when it's at A, the spring is compressed, so this is the force of the spring on block. When it's at B, force of the table on the block, force of the Earth on block. But when it's at B, there's no pushing. Right? The spring is neither compressed nor stretched out, and at C, again, we have the force of the table on the block, the force of the Earth on the block, and here the spring is stretched out, so it's pulling it back. Force of the spring on block. So when I look at this, what we're seeing here is that when it's at A, it has a large acceleration. When it's at B, it has 0 acceleration. And when it's at C, it has large acceleration again, although this time in the opposite direction. So the question says, what happens to the acceleration as the block moves from A to C? Here it's large, the acceleration is large, and so it decreases here and then increases here. So in this section, acceleration decreases because here acceleration is 0, and then here the acceleration is increasing because it's large again. So we have large, 0, then large again, so acceleration decreases and then acceleration increases. And that's because the unbalanced force decreases and then increases. All right, number 3 says, 3 says, what is the amplitude Well, if we look at this here, the amplitude is from the middle out. The amplitude is from the middle out. So this is the amplitude right here. And since the whole distance, it says the whole distance from here to here is 0.4, that means the amplitude is 0.2 meters. Four says, how much time does it take for the block to move from A to C and then back to A? So it's from A to C and then back to A. That time is called the period. And one of the things we know is if you want to calculate the period of a spring, you do 2 pi times the square root of, I'm doing a video, babe, m over k, where m is the mass, k is the spring constant, and t is the period. So if we just plug and chug what we know, it says the mass is 0.5, the spring constant is 50, so do 0.5 divided by 50 in your calculator, then take the square root, then multiply by 2, then multiply by pi, and I got as an answer on this one 0.628 seconds. So it would take 0.628 seconds to go there and back. We call that the period. All right, let's reset the left side of the board here. Okay, we're on number 5. Now, in number 5, it says, how would the time you calculated change if the spring constant were tripled? All right, so since we're dealing with this mathematical model, so here is the spring constant right here. So there's the spring constant. So we're going to quadruple it. So what happens here is we know that the k is in the bottom of this fraction. So because the k is in the bottom of this fraction, any increase in k will cause a decrease in the period. So right away, since it's going to cause a decrease in the period, we know that we are left with multiple choices, D and E here. Also, conceptually speaking, if you increase the spring constant, the strength of the spring, as it slides, it's going to pull it back with more force, therefore it's going to take less time. So we know bigger spring constant should be a smaller time. And so what happens here is I'm going to increase this by a factor of 4. But notice where it is, it's underneath the square root. So if k goes up by a factor of 4, what happens over here? The period goes up by root 4 because it's in the square root. We can see that right there. So the answer would be increased by a factor of 2. So if you, totally a typo. If you increase the spring constant, you decrease the period by a factor of 2. Now, you could always just plug and chug this. 2 pi times the square root of, I'm going to put in the same mass, 0.5, but it says that we have increased this, we've quadrupled the spring constant. So the old spring constant was 50. If I do 50 times 4, that would be 200. And if I put this into my calculator, I end up with 0.314. And if I compare 0.314 to 0.628, we can see that it decreased by a factor of 2. So that's answer D, decreased by a factor of 2. Okay, let's look at 6. 6 says, what would you have to do to the mass to get the time to double? All right, what would you have to do to the mass to get the time to double? So we're going to have to look back at this equation. This is 6. We're going to use the same law here, 2 pi times the square root of m over k. So what we're going to do here is I want to know, what do I need to do to the mass to get the period to double? Well, if I just times the mass by 2, it's not going to work because it's underneath the square root. So if I want to do the period to increase by a factor of 2, the mass would have to increase by a factor of, well, what do I have here? Since it's underneath the square root, it would have to be 4 because the square root of 4 is 2. Another way to do this is to take that original that we had down here. I want the period to double, so I want to do 2 times 0.628 is equal to 2 pi times the square root of m over k. And if you go to calculate that, what happens is you will solve for m is equal to 2 kilograms, and compared to the original, which was 0.5 kilograms, 2 kilograms is 4 times more. So if you want the period to double, you need 4 times the mass. Seven says, what is the frequency? And what's nice about that is we have a relationship with frequency. Remember, the frequency is 1 over the period. So the frequency tells me how often it goes back and forth. The period tells me how much time it takes to go back and forth. So in this case, frequency would be equal to 1 over 0.628. And that's 1.59, and this is oscillations per second. So it only takes 0.628 seconds to go back and forth, which means that it can do 1.6 oscillations for every 1 second. All right, let's reset. That was the first half. Let's go for the second half. So in this one, we have a pendulum attached to a ceiling. And we have a sense that a pendulum can swing like this. So this pendulum swings 20-degree angle, and it's a 100-kilogram ball on the bottom. And the pendulum has some length L. So it says at the Michigan Science Center in Detroit, there's a Foucault pendulum made of a 100-kilogram granite ball that can swing through an angle of 20 degrees when first released and has a period of 9.1 seconds. What is the length of the pendulum? Well, from our lab experience, one of the things we calculated was that if you want to know the period, you can calculate it by using 2 pi times the square root of L over G, where T is the period of time, L is the length, and G is the gravitational field strength. So if I plug and chug this, I have 9.1 is equal to 2 pi times the square root of L, which we don't know, and near the surface of the Earth, G is equal to 10. And if I calculate this, I got L is equal to 21 meters. L is equal to 21 meters. Well, that's not number 1. That's number 8. Sorry. 8. Number 9 says, how would doubling the mass of the ball affect the period of the pendulum? And the answer is, it wouldn't. It wouldn't, which is interesting because a couple things to keep in mind. One, if you look here, there's no mass in this equation at all. So because there's no mass, that means the mass doesn't affect the period. Also, one of the things we know is that if you drop two objects in free fall, the Earth pulls more on the more massive object. But because it's more massive, it's also harder to move. We call that inertia. So those two ideas kind of cancel each other out, and we know mass is not a factor in the swing. Ten says, as the pendulum swings, the angle decreases. And we know that, like, here it swings really big to start, and then a little bit less, and a little bit less, and a little bit less, and a little bit less. So as the angle decreases, how does the time change? And the answer is, right, still 9.1 seconds. Again, if we look at the equation, the swing angle isn't anywhere in here. We know if you pull it back farther, it moves faster, but it also has a bigger distance to travel. As it decreases in amplitude, we have less distance, but we're also going slower. So the time stays the same. Eleven says, just outside of Chicago, there's Fermilab. It says at Fermilab, there's a pendulum that's 4 times as long. How does the period compare? So let's use the same law. So we see that the L is here, but it's underneath the square root. So if L increases by a factor of 4, the period is only going to increase by a factor of root 4, so the period goes up by a factor of 2. Another thing you could have done is you could have solved for it. So we know that the original length was 21, so you could put in an 84 here, 10 here, and solved. If you solve for that, you get 18.2 seconds, which compared to our original 9.1 is twice as big. T goes up by a factor of 2. All right, so that's it for this assessment. Hopefully this illuminates some places that you were strong, some places that you need some work. Work on this, and you will be able to take Harmonic Motion Assessment B this week.